introduce Marco Abbadini from the University of Birmingham, who will speak about Vietoris endofunctor and closed relation and its different view.
Thank you, Luca. So the algebras of propositional model logic are model algebras, and a model algebra is a Boolean algebra with two binary operators, box and diamond, where box is the Morgan dual of diamond, box preserves finite meets, or equivalently, diamond preserves finite joins. Now, of prime interest are free model algebras over a set X, which is the algebra of equivalence classes of model propositional formulas with variables in that set. And but these free model algebras are quite complex. Already, the free model algebra over the empty set has many different elements: 0, 1, diamond 1, and so on. And so it's this free functor from sets to model algebra, which is left adjoint to the forgetful functor, is actually quite complex. But people have figured out how to have a good description of this, nonetheless. And as a first passage, we can break this free functor into two free functors, one from sets to Boolean algebras, and one from Boolean algebras to model algebras, which are left adjoint to the forgetful one. And this is easily understood. The one that requires a bit more of a study is how to add freely modalities to Boolean algebras. And for this, a good way is the step-by-step method. Now, let me first mention that really this free model algebra over a Boolean algebra A has many elements of different shapes, has elements of the Boolean algebra, boxes of this. We can combine an element of A to make a join with a box, and then we can make diamond. But actually, in a certain sense, it's enough to understand just a portion of this free model algebra, consisting of the elements of pure rank 1. So the elements of the type diamond A, box A, and the Boolean combinations of this. Or in other words, the elements where every element of A is in the scope of exactly one modality. And this subalgebra of elements of pure rank 1 can be captured via generators and relations in quite an easy way. So you take the free Boolean algebra over two copies of A, where the two copies are denoted with formal symbols diamond A and box A, and so one for each element of A, modulo the axiom of model algebras, essentially. And this Boolean algebra, so you might think of the element as equivalence classes of Boolean combinations of boxes and diamonds of elements of A, is actually quite easy to understand. For example, there's an algorithm that tells you when two elements are the same, or even more generally and more nicely maybe, when an element is below another one. So if you have two elements of Ka, so two equivalence classes of Boolean combinations of diamond and boxes, there's an algorithm that tells you when the first one is less or equal than the second one. Essentially, you rewrite the elements in conjunctive and disjunctive normal forms, and then you in the end go to a system of inequalities of this type. So on the one hand side, you have a meet of diamonds and a box, and on the right hand side, you have a join of boxes and a diamond. Moreover, with simple manipulation, you can force this side condition to hold, which is essential. And the side condition tells you that on both sides, so let's first look at the left-hand side, the diamond element, each element in the scope of diamond is below the box element B. And same also here. The diamond element C is below each element in a box. So in a certain sense, just for the mnemonics, we can say the diamond is below the box, or if you think of as less or equal as containment, diamond in box. We have also a nice picture of this. And this side condition allows us to have some magic happen, so that this inequality can be rewritten without involving diamond and boxes, and we get this one, which describes what happens in A. So this says that either a diamond element on the left is below the diamond element on the right, or the box element on the left is below the box element on the right. One of the box elements on the right. And so essentially we can name this as the diamond with diamond or box with box formula. And what's interesting about this is that it's it's the most trivial sufficient condition for the above inequality to hold, and quite nicely it's also necessary. This is the formula which can be found in a paper by Seder-Kissel-Cohen about the Vietoris construction, because there's a connection between this K and the Vietoris. And indeed, so K can be extended to an endofunctor on Boolean algebras and Boolean homomorphisms. And now the free functor going from Boolean algebra to modal algebra can be constructed step by step in terms of K. I'm not giving here the construction, but K is enough to construct this functor. And this K has also a nice behavior under stone duality, because it corresponds to the Vietoris endofunctor on stone spaces. Okay. And now we're heading towards our work. The fact is that Boolean homomorphisms are are the main interesting morphisms, but not the only one between Boolean algebras. So we have also this notion of subordination. Now, you should think of a subordination as a less or equal between possibly two different Boolean algebras with the axioms of a less or equal. Now, certain axiom you cannot express, like the reflexivity, because the Boolean algebras might be different. But this one you can. So a join is related to a meet if and only if each disjunct is related to each conjunct. And these subordinations occur in different fields. They're essentially the approximal mappings in domain theory, but also they appear in the region-based theory of spaces. So proximity, contact relations. These are relations that appear often when you consider compact causal spaces. For example, the well-inside relation is subordination. Okay, and just to motivate these subordinations further, they are also well behaved also from a duality perspective, because they are dually in one-to-one correspondence with closed relations between stone spaces. Okay. For our work, our key observation is this. So if you remember these diamond with diamond or box with box formula, now we can interpret this by replacing less or equal with a subordination. And so to every subordination S from A to B, we obtain a subordination from K of A to K of B. We can just replace less or equal here with a subordination S, and then you have to do some work to show that this is well defined. But in the end, what we get, these are contributions. So we extend this assignment K, which captures model formulas of pure rank 1, also to the setting of subordinations, not just Boolean homomorphisms. And so you can compare different K of different Boolean algebras, also in this setting. Moreover, this is not just a random functor, but it is dual to another nice functor, so the Vietoris endofunctor, but this time on closed relations, constant spaces, rather than just on continuous functions. This was introduced recently. And finally, and actually this is the reason why we got interested into this, we managed to answer a question in a paper by 2015. The question was, how do you describe under De Vries duality what is the dual of the Vietoris endofunctor on compact Hausdorff spaces? And by using this endofunctor KS, we get one such description. Okay, and some more details you can find in this paper. I would like also to thank my co-authors, Guram and Luca, who were great to work with. And thank you all for being here.